Hello everyone. A very warm welcome to today's class. Let's start with something fun. Imagine you're at the airport with a suitcase lock. The lock has 4 wheels, each marked with digits from 0 to 9. Now, oh no, you've forgotten the code. You only remember the first digit is 7. That means you need to figure out the rest. Now, will you sit and try all possible 3-digit combinations manually? Pause, chuckle, that would take forever and you might miss your flight. Clearly, we need a clever shortcut. And this is where mathematics steps in through the fundamental principle of counting. It's like the master key that opens not just your lock, but also the secrets of counting without listing everything. So, what exactly is this principle? Let me state it in simple words. If one event can happen in m ways and another event can happen in n ways, then both together can happen in m multiplied by n ways. More generally, if there are k events with possibilities m1, m2, m3 and so on, then the total number of ways is m1 multiplied by m2 multiplied by m3 and so on up to mk. Equation n equals m1 into m2 into m3 dot up to mk. This is called the multiplication rule of counting. And here's the key idea: choices don't add, they multiply. Each new stage expands the possibilities like branches on a tree. Let's test it with a wardrobe problem. Mohan has 3 pants, P1, P2, P3 and 2 shirts, S1 and S2. For pants, 3 choices. For shirts, 2 choices. Now think, for each pant, there are 2 shirt options. So the total outfits is equal to 3 multiplied by 2 equals 6. If you list them, P1 with S1, P1 with S2, P2 with S1, P2 with S2, P3 with S1, and finally P3 with S2. Exactly 6 combinations. That's multiplication principle in action. Simple, fast, and neat. Now let's move to Sabnam's school problem. She has 2 bags, 3 tiffin boxes, and 2 water bottles. First, she picks a bag in 2 ways. For each bag, she can pick one of the 3 tiffins. That's 2 times 3 equals 6 ways so far. Then, for each of those 6, she has 2 bottle choices. Multiply again, 6 times 2 equals 12. So Sabnam has 12 possible ways to walk to school with her bag tiffin bottle combo. See how the choices multiply step by step. It's like building a sandwich layer by layer. The more layers, the more variety. Let's spice it up with letters. Take the word ROSE. We want to form words using all 4 letters without repetition. First place equals 4 choices. Second place equals 3 choices left. Third place equals 2 choices. Last place equals only 1 option. Multiply 4 into 3 into 2 into 1 equals 24. In factorial notation, 4 factorial equals 4 multiplied by 3 multiplied by 2 multiplied by 1 equals 24. So, there are 24 possible words with or without meaning. And notice, writing them all would take a lot of time, but the counting principle does it instantly. But life isn't always so restrictive. Suppose repetition is allowed. Then each of the 4 places can be filled with any of the 4 letters. So, total words equals 4 into 4 into 4 into 4 equals 4 raised to the power 4 equals 256. Compare, without repetition, only 24. With repetition, 256. That's a giant leap. This shows how important it is to check the condition: are repetitions allowed or not? A small change doubles, triples, or even explodes the count. Let's play with numbers now. Suppose we want to form 2-digit even numbers using digits 1, 2, 3, 4, and 5. Repetition is allowed. Start with the units place. Since the number must be even, the units place can only be 2 or 4. That's 2 choices. Now, the tens place can be filled by any of the 5 digits. That's 5 choices. Multiply 2 times 5 equals 10 numbers. Now, try colorful flags. 4 flags of different colors, arranged 2 at a time, one below the other. The top slot equals 4 choices. The bottom slot equals 3 choices. Multiply 4 times 3 equals 12 signals. Whether it's numbers, words, or signals, the principle works the same. And that's the beauty of mathematics. It's universal. So let's wrap this up. The fundamental principle of counting says, when independent events occur in sequence, the total possibilities are the product of choices at each stage. We saw it with pants and shirts, with Sabnam's bags, with the word ROSE, with repetition allowed, and with even numbers and flag signals. This principle is the foundation of permutations and combinations. Once you've mastered this, you're ready to explore advanced formulas and applications. And that, my friends, is how mathematics turns big, messy problems into clean, simple answers. In the next session, we'll step into permutations, where order matters, and see how this principle naturally leads us there. Stay tuned, it gets even more exciting.